Hello, my name is Kaya Mitchell, and today I'll be presenting my Physics 2 lab. Newton's second law states that the acceleration of an object is dependent upon the net force acting on an object and the mass of the object. When a constant force acts on a massive body, it causes it to accelerate, or in other words, changes the velocity at a constant rate. Gravitational force due to gravity near the Earth's surface is the free fall of acceleration of an object that experiences no air resistance. The value for this acceleration has been found to be 9.8 meters per second squared. However, typically when an object falls through the atmosphere, it is subjected to two external forces, both the gravitational force, expressed as the weight of an object, and the drag force, which depends on the square of the velocity. In this lab, I examined and analyzed the motion of a falling object in order to identify and model the interactions that occurred during its motion. This lab consisted of me extracting data from a video of a falling object, constructing models using Newton's second law, and comparing the prediction of these models with my observations. The answer to this lab is important because it shows the relationships between forces and motion and allows us to calculate the acceleration and therefore the velocity and position of an object, which is incredibly valuable to scientists, engineers, and inventors. The result of this lab proved that it is possible to model and predict the future position and motion of an object experiencing non-zero forces by knowing its initial position, velocity, mass, and net force. When examining the motion of a falling object, in this case my dog's Chuchoy, the video was recorded at 30 frames per second, and the height of my staircase, that stood at 1.9 meters, was calibrated to the length scale in the video. The coordinate system was then chosen to be at the origin of the center of mass, and I had to tilt the coordinate system in order for it to move in the direction of the motion, which pointed in the negative y direction. From the video analysis obtained, the observed position of the object as a function of time. The motion of the toy is observed for a duration of 0.6 seconds every 0.33 seconds, and the start of the analysis was at 0 seconds, where the object is located at the origin and is at rest, moving with zero velocity. I then weighed my object of interest with a mass scale at home and plugged this value into ball.m. Next, I had to use Newton's second law in order to construct a computer model that would describe and predict the observed motion. In this case of motion, the velocity is changing, meaning that it is non-constant and the change of velocity is non-zero. So this therefore suggests that the net force is non-zero. This indicated that there is an outside force acting on an object, and in this case, it is gravity, which is in the negative y direction, where gravity equals weight, which is the ball's mass times gravity times its direction vector. However, to model the system more accurately, we will be taking air resistance into account, where air resistance equals the drag force constant b times the velocity squared and its direction vector, which points in the positive y direction, as opposed to gravity. This makes the net force in the y direction equal to the sum of the drag force minus the gravitational force, which is what we will use to update the object's position with the graph with drag. And the graph without drag, I will be using this code. Here are the results from the data collected from my experiment and the graph of the model with and without drag. As you can see, both of my computational models differ from the setup. What is interesting is that both the model with and without drag are almost identical, suggesting that the value I found for B to use in this model was extremely small to the point where drag force was equal to 0. However, we know that this is not true because my real-world data shows that there is at least a little bit drag acting on the object. I believe that the cause of this deviation in my data could be from errors in my data collection that could be from an inaccurate value for B, or not allowing my object to fall for a long enough time to experience air resistance, or simply my object's mass was too large for it to experience drag force in the time interval that it was recorded in. But overall, I would say that the computer model does a pretty good job in modeling an object's motion falling to the ground. When an object is falling to the ground and only being acted upon by gravity, the change in the object's velocity would be constant, so it will never reach terminal velocity, because the magnitude of velocity will continually be increasing until another force is acted upon it in the opposite direction. An object will reach terminal velocity when the force of gravity is equal to the force of drag, so there has to be a drag force present. Hence the reason the model with drag force would be the ideal model to predict terminal velocity, even though my data does a poor job of reflecting this principle. If we were to increase the initial velocity of an object by throwing it downward, it would not affect the terminal velocity, and this is because terminal velocity is not dependent on the initial velocity. Side note, I did not represent this data with my own computational model because my model poorly reflected the drag force constant. However, starting with an increased terminal velocity makes an object reach terminal velocity faster, but not change the value of terminal velocity. Overall, I thoroughly enjoyed this lab, and I felt that I gained a better understanding of Newton's second law by going through the experimental process of this lab. Thank you for learning physics with me, and I hope to see you next time. Bye!